Hello again. Welcome to the first of a four-part series covering kernels. In this video, we'll discuss why we need kernels. The slides for this lecture were written by Sebastian Urban. This means that the notation in this lecture series differs from that used in the linear regression series. But if you're familiar with linear regression, this notation should be fairly intuitive. I also want to start off by apologizing that these slides are really full. And it might make it a little difficult to view when you pause the video because of those little window bars that pop up. Anyway, these slides were created with the intent of having all the information that you need on them. That means that they're going to be a little dense. Here in the notation, I've tried to give a conversion between the notation that I used in the linear regression slides and the notation that is used here. Hopefully this helps with any confusion that we see between the two notations. The major differences are that instead of using subscript to denote a specific sample, we see this bracketed superscript. Furthermore, our target variable is z from our previous lecture series is now denoted as y. Also make sure that you don't confuse this with the function y, which is our output computing function that we should already be familiar with. The only other major difference is how vectors and matrices are identified. In this lecture, vectors are bold, and matrices are uppercase and bold. This is a slight deviation from what we're used to from the last lecture series. So imagine we want to find out the correlation between the temperature outside and the number of chirps per second that a cricket chirps. We even have some data, as we can see here in this plot. And, like any good biological data set, every data point is affected by some sort of noise. If we were lucky, we'd be collaborating with a biologist that could give us a model for the rate of chirps that takes into account biological constraints of the cricket. For example, perhaps the biologist knows that as the temperature goes down and gets cooler, the cricket will chirp less because of a biological constraint regarding heat and the chirping mechanism. They could also know that if the temperature of the insect gets beyond a specific range, then the insect will die. All of this is useful information for our model. But since most of us are not biologists, or at the very least we're not entomologists, what can we do to make our predictions? Can we still make predictions on this data? Well, of course we can still make predictions. We can use knowledge we gained in linear regression lectures to fit a model to the data that we have. So given our data, shown by the blue points here in the graph on the left, we can fit a linear model to the data. That is, y of x equals ax plus b, which we all know we can rewrite into a different form, which is y of x equals w transpose phi of x, where w is our vector of weights and phi of x is our basis function. And, as expected, we can use a squared error to fit the data to the model. We fit this model by calculating the error, which we can see here in matrix form, and we can minimize the error by taking the advantage of the Moore-Penrose pseudo-inverse. This should all be reviewed from the linear regression lectures. So what's the problem of using this method? Well, once we get outside the bounds of the data points, this method doesn't extrapolate very well. Here's a good example of another case where linear extrapolation can produce terrible results. In the last lecture, we got a better fit to the data when we used a higher level polynomial. Do you think that approach works here as well? Well, the answer with this data is no. We see that the model is overfitting. That is, it's just fitting itself to the noise in the data. We get a worse fit to the data, and the complexity of the model has gone up. Why does this happen? Well, it's simply because the assumption that we're making with our choice of model structure doesn't match the data. In other words, our data isn't originally generated by a higher level polynomial. So, what can we do to combat this? In our linear regression lecture, we talked about several options to combat overfitting, such as regularization. But how is regularization going to help if our underlying assumptions about the function that generated the data are wrong? Are there any basis functions that we can use that work decently well for any problem? Let's consider the following option. What if we thought of our training points as delta functions? Now, instead of keeping them as delta functions, we increase the width of the functions so that they resemble Gaussians, like you see in this picture. If we then sum over all of the bumps that these Gaussians make, we get smooth interpolated functions. We could also consider the case when we don't center these Gaussian-like functions on the data points themselves, and we would get a similar looking formation. One way of doing this is by the use of what are known as radial basis functions. In this case, let's look at what happens when we convert our bumps into actual Gaussian representations. We get Gaussian radial basis functions. Here, m determines where the mean of the Gaussian is located, and alpha determines the variance. Though the value of a Gaussian RBF is given by a Gauss function, like the probability density function of a Gaussian distribution, the covariance matrix is a scaled identity matrix. Due to the fact that the exponential function declines very fast to 0, Gaussian RBFs have no long-range interactions. Consider the plot on the lower right. The red line is the sum of the two RBFs. While the two Gaussian RBFs interact in the middle of the plot, the function value of the sum beyond negative and positive 1/2 is 0. This is a very nice property compared to the polynomials where the value of the function usually goes to positive or negative infinity as x grows. Here's just a plot of a Gaussian RBF formed by two parameters so that you can get a feel of what this looks like by seeing its radial symmetry. So let's use RBFs to try to tackle a problem similar to the one that motivated our discussion in the linear regression lectures. Here we have a true generating function modeled by sine 10x with data points that are corrupted by noise. Let's try to approximate this function using 16 Gaussian RBFs. Skipping the actual calculation work, we can see that the basis functions do a pretty decent job of fitting the true underlying distribution. Awesome! We have a nice universal approximator. Time to sit back and rest for the rest of the semester. But wait a minute. What if we have a problem with higher dimension? Does this still scale? As you might have expected, no. It doesn't scale that well. If we want to cover the input space with equally spaced RBFs, every dimension increases the number of required RBFs by a constant factor. So, if we need 16 RBFs in a one-dimensional space to get a good regression, we already need 256 or 16 squared RBFs in 2 dimensions. Remember, we need 1 weight per basis function. So, for 5 dimensions, we already need to store 1,000,000 weights. Calculating the pseudo-inverse of this 1,000,000 weight sample would take on the order of 16 to the 15 operations. This is clearly not feasible. Check out the next video in this series to see how we can tackle this problem.